Hello everyone. In this video, we are going to talk about capacitors. Now, again, most of you might know capacitors and use them. So here I'm trying to provide as much information as possible regarding capacitors to you. And if there is a part that you know it, you can fast forward. So capacitor is another passive element that, of course, does not need to be charged or anything. Actually itself is a storage of electric energy. So it stores energy in the form of an electric field inside of it. Okay, and it basically has two plates in general that when you attach them to a battery, right, then one side of it will get all the positive charge, the other side gets all the negative charge, and there will be a constant electric field between them, and there will be some voltage across that voltage of capacitor, and so it gets charged, and then if you cut the circuit and open it, it can be discharged, so it acts as a storage. In fluid systems, you can look at it like basically a tank or something that stores the fluid. So it stores the energy here. And inside of these two metal plates, typically, or other types of plates that you have that can hold the charge, in between these two plates, in order to make it have more charge, they put an insulator called dielectric. So inside of this is typically filled with some kind of material. We call it dielectric, and dielectric is an electrical insulator, which if you apply the electric field between these two plates, it can also be polarized. So it can make this field stronger, and it can basically allow more charge to be, if we call this Q, these charges, it allows more charge to be stored and held on these plates, okay? Because it can also be polarized. So this is a simple capacitor. Now you can see their shapes. They are kind of like barrel shape, many of them, but not all of them. Some of them are kind of like a lentil, you might call, right? The ceramic ones. And there are other ones. There are even ones that are variable, okay? And so on. But you have the ceramic ones, you have this basically electrolytic ones, and so on. You have the super capacitors and so on. So there are all sorts of it. And here we're gonna look at those types at the end of this video. But if I want to give you a similar thing in a fluid system for charging and discharging a capacitor, I can talk about a pump which is connected to basically this member with a flexible membrane inside. Because what happens, as we'll see, when you here, if you have a key, when you connect and start the charging of the capacitor, if you look at the voltage of the capacitor versus time, you see that the voltage is initially 0, but soon it is going to start going up and ultimately reaching this velocity, this voltage, sorry, of the supply. Okay, exponentially it is going there. And the speed of that depends on the capacitance C, which we'll talk about, and this resistor R. Good? If you open the circuit, then it is going to go down. So from this high voltage, it is going to go exponentially down and so on. And initially, when the circuit is closed and there is no charge, the thing is, it shows no resistance. So initially, if you look at how much resistance a capacitor will show, initially it shows no resistance. So the current through the circuit, it is going to be some non-zero value, but initially, although the current is big and it allows the current to go, but over time that current subsides and goes down. And ultimately, when this capacitor is fully charged, Now it acts like another battery in the system that is in the opposite direction of your supply voltage. And so because these two are equal, you see it reaches that level, the I is going to go to 0. So you say that finally your capacitor shows infinite resistance. So initially no resistance, initially there is current, but over time the resistance gets bigger and bigger for this capacitance and the current goes to 0. So in a mechanical system, if you would, this is similar, as I said, to a pump that starts pumping. When it does, it applies some pressure here on the top of this membrane and will distort it. Although no fluid here goes from this top portion to this bottom portion because there is a membrane in between, but because this flexible membrane is distorted and deformed, right? So initially it was like this. Now it is deformed. It is going to push the fluid in here and start some fluid. So some m dot is going to start through this system a little bit. But over time, since this side keeps building pressure, ultimately the pressure here and the pressure from the top, which comes from the motion of the pump, ultimately these two become equal. So over time, this deformation of the membrane starts going back, and finally the membrane ultimately goes back to what it was, and this m dot will go to 0. Okay, so this is an analogy that you can have in a fluid system for the behavior of a capacitor during charging and discharging. Good. So the first thing is, how do you calculate what we call the capacitance of a capacitor? And what does this capacitance have to do with the charge on the plates and the voltage across the capacitor? So the capacitance of a capacitor, C, is defined as Q over V, where Q is the charge on the plates, V is the voltage across it, and C is the capacitance. The unit for the capacitance is called farads. So it is measured in farads, microfarads, nanofarads, picofarads. Okay? Now, this capacitance itself, this C, it depends on the structure of the capacitor. So in very simple shape, if the capacitor is made of two plates, each one with cross-section A and a separation or distance D, then the capacitance is going to be epsilon naught A over D. So C is going to be epsilon naught A over D, where A is, again, the cross-section of the plates, D is the distance between them, and epsilon naught is what we call the permittivity of free space. So this is assuming that there is nothing between these two plates. It's vacuum. If there is nothing between them, then the capacitance is epsilon naught A over D, where epsilon naught for free space is this constant number, 8.854, 10 to the negative 12 farad per meters. Okay? But most of the time, as I said, you fill between these two plates with a dielectric. Okay? You fill it with something to make it stronger. So whatever material that you use between these two plates, it can make this epsilon naught bigger. So it comes with its own coefficient, epsilon r, which is bigger than 1. And this epsilon r is the relative permittivity of that dielectric, or the dielectric constant. And it's bigger than 1, so it makes your capacitance be bigger than the scenario that between the plates it was empty or nothing between them. Okay, so depending on which material we fill the capacitor with, this epsilon r will be different, and A and D. So if you want bigger capacitance, you need bigger plates, you need to get them closer to each other, and you need to fill them with stronger dielectrics, with bigger dielectric constants. Then you get bigger capacitance. Now, most of these capacitances, as I said, they are mostly in microfarads or nanofarads or picofarads. If you see something like 1 farad, that's not super common. That's a huge capacitor. Okay, that's a huge amount of capacitance. Most of the capacitors, if you look at the ranges, the ones that we use in typical applications, they are in microns. Okay, So getting something that can go 1 farad, that is like a very, very large number. Just keep that in mind. So this is the capacitance formula, and this is the relation of capacitance with charge on the plates and the voltage. Now, many times in controls, electric circuit, mechatronics, you need to find relation between voltage and current. Okay, now you know that the relation between current and charge is integral of current per time, because current itself is the time derivative of the charge, correct? So if I replace that Q with integral of I over dt over V, then you see the relation between capacitance, electric current, and voltage. And if you swap C and V, here is the voltage current relation. V is integral of I dt over C, or if you take time derivative out of this, then you see that the current through a capacitor is C dV over dt. Okay, so C, constant of the capacitor, capacitance, times dV over dt is the current. So if you go back and look at that charge graph that I did for you, remember I said that the voltage goes like this when you charge it, and the current goes like that. Does it make sense? Yes, it does. Why? Because as you get closer and closer to the steady state voltage, your dV over dt is going to go to 0. Your V is almost becoming a constant. That means I here is going to 0. Okay, so the faster the V changes across a capacitor, the bigger current goes through it. And when the voltage goes to constant across a capacitor and doesn't change anymore, which means it cannot attract more current, more charges, then of course I goes to 0. Okay, so it depends on how much charge you can store on it. The more charge, the faster the charge is stored, the bigger the current is, of course. Now, another thing that we need to talk about, as I told you, is between the 2 plates of a capacitor, there is an electric field, E. So how do we calculate this E, the electric field that is between the positive side and the negative side, this E? How can we find it? Well, we can show that E for a capacitor comes from this formula V over D, where V is the voltage across the capacitor and D is the distance or the separation. Okay? So if we bring them closer, we have a bigger electric field. If we have bigger voltage, we have a bigger electric field. Now for V, we can replace it by Q over C based on the definition. D is there, so it's going to be Q over CD. And what was C? Remember, the formula for C is this guy. Epsilon R epsilon naught A over D. So when I multiply C by D in this denominator, those 2 D's would cancel, so CD is simply epsilon naught epsilon R times A. So it's going to be this one. And now here this Q over A, the charge per surface area, this guy is what we call sigma. Okay, sigma is the charge per area or density of the charge on the plates. It's the charge density on the plates. So if you divide that sigma by epsilon R epsilon naught, that is also another way to say that is the value of electric field. But most of the time, the formula that we use is V over D. So this is the most common formula that we use, although we can use this one as well. But most of the time, the ones that are easily measurable are V and D, because D we can find from the data sheet and V we can read from a multimeter. So just by measuring those, I can get what? I can get my electric field. And the question is, where does this formula come from in the first place? Well, that comes from what we call the Gauss theorem. So one of the fundamental theorems in electromagnetism is Gauss theorem, which says the integral of EdA, or integrated over the entire area that E is passing through, is equal to Q over epsilon. So it says if I have some charge Q and this Q creates some electric field which passes through some surface. So that is your A. E dot dA, which is the normal electric field passing through these small elements. So if I have some small elements here, dA, E dot dA, the normal component of E along dA, if I integrate it over entire surface, that should be equal to the electric charge that made that E divided by epsilon naught. Now in this case, the area that you have is the area of this plate. And since AE is normal, as you can see, E is normal to the A, this integral of EdA is simply going to be E times A. This is equal to Q over epsilon naught. So from here, E is going to be Q over A epsilon naught, which is exactly this part here. You might say, what about that epsilon R? Well, here, this formula that we used, this green formula, this Gauss formula that we used, Gauss theorem, this is assuming that inside this area is vacuum. There is nothing. If I fill it with a dielectric, then I have to add an epsilon R here in the denominator as well. So it's going to be like that. And this guy is the same as what? This denominator is, of course, C over D, C times D over Q. And then Q over C is what? Is the voltage. So it's going to be voltage over D. So you see this V over D comes actually from what? Comes from the Gauss theorem. If you start from the Gauss theorem, you can end up with this important formula. So this is how you find the electric field inside a capacitor. Okay, let's move on. So similar to resistors that we had them in parallel and in series, we can have the same thing for capacitors parallel in series and find an equivalent. How do we do that? So if they are in series, their equivalent is going to be sum of them. If they are in parallel, if they are in parallel, equivalent is sum of them. If they are in series, then 1 over equivalent is sum of the reciprocals. So this is exactly the opposite of resistors. Resistors, the summation was in series. This sum of reciprocal was in parallel. You see, capacitors are exactly opposite of resistors. Now, where does this formula come from? I can show you. So, and when I say equivalent, I mean replace that with a single one. So replace all of that with one single capacitor, which is called C total or C equivalent. Okay, so if you do that, these two are equivalent. Now, where does that formula come from? Well, remember that in the case of parallel circuits, the voltage across all of these capacitors are all the same and they're all equal to V. So I can say that V equals V1 equals V2 equals V3. Yes? That's obvious. Now, let's look at the charges. In this case, if I say how much charge is stored on this capacitor, you say Q is equal to what? Q is equal to basically the C total times what? Times the V. Correct? That's the total charge that is stored on that equivalent capacitor. What about this bottom case? In this bottom case, your total current is split into 3 separate currents. So you can say that your total charge Q is split into separate Qs, Q1, Q2, and Q3. And since sum of these I's equals the big I, I can say sum of these smaller Q's is equal to the big Q. So the big Q in the equivalent circuit is equal to sum of these individual Q's of these parallel capacitors. Now Q, you know, is equal to C times V based on the relation. So Q total is C total times V. Q1 is C1 times V1. This is C2 times V2, and this is C3 times V3. But guess what? The voltages are all the same, so I can get rid of them. And there we go. C total is C1 plus C2 plus C3. You see? Not a big problem. Okay? So clearly, that's how you show some of the individual ones is C total. And that means, of course, C total is bigger than all of the individual C's. So if you want to get bigger capacitance, what should you do? If you want to be able to store more and get bigger capacitance, you need to put capacitors in parallel. On the other hand, if you put them in series, this is the formula that you have, and in this case, you can say that C total is less than all individual C's. So here you reduce the total capacitance and the storage. And again, it's not really hard to show for this case as well. So in this case, the total voltage drop V is equal to sum of the individual voltages, right? You can see if you go around the loop, V equals V1 plus V2 plus V3 in this series circuit. What about Q? If I say those are all equivalent to a single C total, then the charge that goes on this should be the same as all these individual ones. Why? Because that charge is coming from electric current I, and here this I is the one that goes through each and every one of them because they are in series. So in this case, I1 is the same as I2 equals I3 equals I, and when you integrate them versus time, what does it mean? It means that Q1 equals Q2 equals Q3 equals Q. Yes, their charges should be the same. And what is the charge? Remember, the charge is C times V. So this is equal, and here for the V, I'm going to replace it with what? I'm going to replace it with Q over C total. V1 is going to be Q1 over C1. V2 is Q2 over C2. And this is Q3 over C3. But remember, the Q's are all the same. So if you simplify, you're going to get to this relation here. Okay? So that is the equivalent of capacitors in series. Now, let's talk about types of capacitors. So there are a bunch of different types, and many of them are typically constant capacitance. The last one is the one that is variable one. But the constant ones, the ones that are the cheapest and simplest, are the ceramic ones that, as I said, look like kind of a lentil. Their capacitance is small. They are small in size as well, and they are stable but low cost, and they are used for signal filtering, decoupling, and so on. Then the ones that are typically filled with an electrolyte, a chemical or gel type material, to give it higher capacitance. So that dielectric is typically a liquid or gel type. And of course, the plates are made of metal. They have bigger capacitance. One thing very important about them is they are polarized. What does it mean? It means like in this capacitor, this ceramic one, if I connect this side of it to the positive of the battery and this side to the negative, or next time I do this side to the negative, this side to the positive, there is no difference. It doesn't have any preference in the direction of connection or polarity. But these ones, these electrolytic ones, they have a polarity. If you look at their body, there is a negative side and it is marked, okay? And typically, if you look at their legs, one of the legs is shorter, the other leg is longer. The longer leg is the positive leg, the shorter leg is the negative leg, okay? So you have to make sure this side is always attached to positive of the battery, this side is always attached to the negative. If you do the other way, they are not going to be happy, and by not happy means they are going to explode many times. And if they explode, they can hurt the electronics, they can hurt you, and so many other things. So you need to make sure that you observe their polarity. They are very amazing, but you have to observe their polarity if you don't want anything to get damaged. They are used in audio circuits, they are used in power supply filtering, and so on. And then there are the ones that have tantalum material, tantalum oxide. They are really reliable and stable. They are compact, so they are kind of like these lentil ones, but they are bigger. Their appearance is mostly kind of like this, and they are used for space and medical applications that you need some capacitor that is really reliable and compact size, because the ceramic ones are not as reliable. So you need it to change very, very slightly from the nominal value, and you need it to work a lot. So we use the metal tantalum. And then there are the ones with plastic film that they look kind of like this. Okay, they are kind of like the headrests that you have in your car, I would say. The good thing is their loss is very low and they are very high precision, so you can use them in motor controllers and timing circuits. Then there are these ones that are very similar to these electrolytic ones. We call them supercapacitor. There are carbon-based material in them. Their capacitance are very high and they charge very fast. Okay, so if you want very large capacitance, you need to use these supercapacitors, and they are used to store energy and used for backup of power. Okay, so if you want to charge something and use it over time, you have to use a supercapacitor. And of course, there are the ones that their distances or the plates can move, and they are filled with air and ceramic or plastic. These are variable. Their plates can move. So their capacitance can be adjusted, and they are used in tuning circuits, in radio tuning and frequency adjustments, and they look like that. Okay, so there are all sorts of different capacitors in the market. By the way, these pictures are coming from Wikipedia. Okay, so I directly got them from Wikipedia. So credit goes to Wikipedia. Now, a few other things about capacitor before we finish this video. Now, you remember resistors, they have these color bands on them that by looking at them, we can read the resistance. Capacitors, some of them directly written, the number is directly written on it. I mean, if you go and look at one of these, okay, I don't think you can see it here. If I zoom into this one, probably you can see the number here. Let me see if you can read it or not. But if you look at that, it says 47 microfarad. So for many of these capacitors, the number is directly written on it, okay, with the units. For some of them, you're not going to see direct number, but you're going to see something like that, a 3-digit number, where the first two numbers are the significant figures, and the third one is the power of 10. So if I see 103, that doesn't mean 103 microfarad or nanofarad or anything. What does it mean? It means 10 times 10 to the 3. And the unit of them are picofarad, 10 to the negative 12. So this is 10 to the 4 times 10 to the negative 12, which is 10 to the negative 8. So I can write it as 10 times 10 to the negative 9, or 10 nanofarad. So that guy is 10 nanofarad. Or if it's 742, that means 47 10 to the 2 pico. So that is going to be 4.7 nanofarad. So if you want bigger numbers, this last number really should be very large. Okay, the ceramic ones in general, they are small capacitance. You see, they are in nanos. If you want to get something in millis or something big, you have to use these supercapacitors. And these guys can go to microns. So these are mostly nanos, these are microns, these can go to millis and so on. Okay, so this is how to read the number for them. I talked about the charging and discharging of an RC circuit. So if you have a capacitor and you have a resistor, we call it RC circuit, then what you can do, you can charge and discharge it, okay? And if you charge it, the voltage across that is going to be Vmax, where Vmax is this here, 1 minus e to the negative t over tau. This tau is called time constant of the system, and this is the time that your voltage is going to be about 63% or 63% of the voltage, the final one. So your voltage versus time is going to be an exponential increase until it reaches to this, and typically about 4 time constant is where you are almost at 99 point something percent of the final value. So typically you need 4 time constant to reach to almost the final value. And for the RC circuit, this tau is equal to R times C. So if you use bigger R or bigger C, that increases the time constant and increases the time for the system to be charged. If you use a smaller R or a smaller C, you can get the capacitor to charge faster and also discharge faster, because the equation for discharging is an exponential decay, as you can see. So it's Vmax times e to the negative t over tau. So it goes to 0, it starts at Vmax, and again at about 4 time constant, it is almost at 0. Okay, and you can easily derive these equations for charging and discharging. And I guess in this case, this R should come here, not there. So because that changes the circuit. So this is a series RC circuit where the voltage is across the capacitor, and this is this voltage that you measure. And these are the equations for charging and discharging, and it's not really hard to show. I'll show you in a second where I talk about this reactance. I'll derive those equations for you. So what I need to explain the next is reactance of a capacitor. Reactance is the imaginary opposition or the imaginary resistance of capacitor to AC signal. So opposition to AC signal, this is also what we call the imaginary resistance. And it is the voltage in the Laplace domain over I in the Laplace domain. In circuits, you might also call it impedance, and that is 1 over CS. Okay, how? I'll show you. And then in the frequency domain, it is going to be 1 over, for S, you replace it with j omega. So it's going to be 1 over Cj omega. And then for omega, because omega is a frequency in radians per second, you can replace it by 2 pi f, where f is the frequency in hertz. But omega is radians per second. So that's the next thing we have for capacitance. That is what we have. Now pay attention that I said this is the same as impedance here. It is, because it's just a pure capacitor. But in general, impedance Z is equal to resistance plus J times reactance. And reactance most of the time is shown by X. Okay, so the reactance and impedance are two different things. If your components, if your circuit has actual physical resistance, that the one that generates heat, that is the real part of your total resistance. The imaginary part of your resistance, as I said, is called the reactance. So the total reactance and resistance all together is called impedance. But X is just the imaginary part of it, and R is the real part of it. Now, for a capacitor, since there is no R, reactance and impedance are the same thing, except that the reactance does not have this J part. So the reactance for a capacitor is simply 1 over C times omega, not 1 over Cj omega. Okay, so this is the reactance for a capacitor. but the impedance for a capacitor is 1 over Cj omega. So this is the difference between reactance and impedance of what? Of a capacitor. So if we want to hold the correct notation here, we have to change that to X of C, because Z of C is V over I over there. So we can add it over here. So the reactance is 1 over C times omega, or in terms of frequency, 1 over C times 2 pi F, where F is in hertz. But impedance, there is an extra J here that we have to add. Okay, so we don't want to mix these two together and say that reactance and impedance, they are the same thing. They are not the same thing. Okay, now what's the application of impedance or reactance here? So we can treat this whole system and remove this capacitor and put an imaginary resistance here where that is 1 over C times S. So we can use the reactance of it, and this is R. And this is V in, and this is V out. Right? So, and the current, let's say, going through is I. So it is not really hard to show that. Since these are like two resistors in series, the total resistance is sum of these two. So if you divide the total voltage by sum of these two, that will be your current. So I here is your V in divided by R plus 1 over CS. And then V out is simply just the voltage across the capacitor. So it's equal to its imaginary resistance times the current. And if you eliminate I between these two, right? So basically for the I, plug this right down here and find V out over V in, or the transfer function in this system. You see that it is going to be 1 over 1 plus RCS. So this is your transfer function in the Laplace domain, and remember that we call this guy here, this R times C, we called it the time constant. Okay, so if it's 1 plus tau times S, right, then you can find solution here. So assume that this V in is just a constant number like V max. So V in of time is just V max, some fixed number. Then these are the S domains. So in the S domain, V in is going to be V max over S. And if you cross multiply, you see that V out in the S domain is going to be V max over S times 1 plus tau times S. Okay, and then if you take Laplace inverse from both sides of this, clearly your V out in the time domain, the voltage across capacitor in the time domain, as you know from Laplace inverse, that is going to be this guy. Okay, so you see, easily you can get that. And of course, in the discharge scenario, V in is 0, so you only get the K component. So you see that using this reactance, I could easily form my transfer function. I could easily find the output voltage to a constant input. Now, if your input is not constant, if it's harmonic, then you find the Laplace for the input in the input voltage. You find the Laplace of that, plug it in, find the output Laplace, and then take inverse Laplace from both sides, and you find the solution as well. So as long as you have this transfer function, which is what really is important, once you have that, you can see for different inputs what kind of outputs you are going to get, because this is a linear system. And if you cross multiply also, you can see that the differential equation is a first order, because you only have s to the power 1. So this is a first order system, of course. Another application of that is, now that you have the transfer function, all you need to do, remember the transfer function was 1 over 1 plus RCS. That is your transfer function, which is V out over V in. Now, if you want to know what this system does in the frequency domain, this system, what you need to do is wherever you have S, you replace it with j omega. So your G of j omega, the frequency domain, is going to be 1 over 1 plus RC j omega. And this one has a magnitude and it has an angle. Now, for filters, mostly we care about their magnitude. So what we want is magnitude of this. And of course, magnitude of 1 is 1. This is a complex number, so magnitude of it is the real part squared plus the imaginary part squared. And this is going to be the magnitude, this function here. And if you plot that versus frequency, you see this is going to be the plot of the magnitude. So this is the magnitude of the transfer function. And if you want, you can take 20 times log of that. So instead of showing magnitude of G of j omega, you show 20 times like 10. Okay, if you show 20 times like 10 of that, then the unit of that is going to be decibels. Now what happens? Look, if omega is 0 at the very left side, this whole thing will be 0. It's going to be 1 over 1 is 1. And log of 1 is 0. So you're going to get 0 decibels when omega is 0. And as omega gets bigger and bigger, then this linear term this constant term 1 is not comparable to this. So you can neglect it. And then your magnitude will literally go to what? It is going to go to 20 like 10 of 1 over magnitude of RCJ omega, which is simply RC omega. Okay? And of course, you can write this as RC omega to the power negative 1. And this is your constant, but here this negative 1 can come behind the logarithm and it becomes negative 20 like 10 of basically RC omega. So you see that in the log space, it is going to go to a line with a slope of negative 20 decibels per what we call decade. And that is this line that you can see when omega gets big. And at some point, there is what we call a corner frequency, a breakpoint, a cutoff frequency. And that is when the magnitude of G of j omega becomes equal to 1 over square root 2, which is equivalent to the energy of your inputs to be dropping by 50%. So if the energy of your input signal drops by 50%, the magnitude should be 1 over square root 2 because energy is proportional to magnitude squared. Okay? It is proportional to magnitude of G squared. So it is going to go down to 50%. If you set this square root, if you set this guy, if you set this equal to 1 over square root 2, that is what we call the cutoff frequency. And for that, your cutoff frequency is going to be 1 over RC. So you see the value of the capacitance determines the cutoff frequency. And what is cutoff frequency? Basically, in cutoff frequency, in ideal filters, what we do is we say that above that, you see the attenuation is very small. The amount of decibel is a small negative number, so it is not filtering out a lot of these frequencies below cutoff frequency. But after that, since it's a big negative number, you are going to get what? You're going to get big attenuations. So your energy of the signal drops by more than 50%. And if you just look at the magnitude without taking 20 log, you can approximate that by something like this. Ideal case. This is an ideal low-pass filter. The one that you see in this picture, that is the actual low-pass filter. So you say above this omega cutoff, or omega B in this case, which is 1 over RC, it allows everything to pass. After that, it is gonna basically take all of the energy of the signal out. Okay, in reality, we never get this perfect thing. As you can see in this case, we get something like this. So this green one is the actual magnitude of G of j omega. This is the decibel version of that. So here the y-axis is 20 log 10 of magnitude G as opposed to just magnitude G. Here, this is just magnitude G. So what you will get is what we call a low-pass filter. It does not change the magnitude of signals for which the frequency omega is less than your cutoff frequency too much. But if your omega is bigger than the omega cutoff, then you're going to see a big attenuation. So if you put the capacitance on the output and resistance in series, this is what we call a low-pass filter. On the other hand, if we swap the resistor and the capacitor and put the resistor as the output and capacitor in series, your transfer function here, you can easily show that in this case, your transfer function G is going to be S over 1 plus RCS. And if you plug in for S j omega and take the magnitude of it, this is going to be the magnitude. And if you plot this case, forget about this decibel for a second. If you plot this case, this magnitude of G versus omega, you see that at omega of 0, the numerator is 0, the whole thing goes to 0. And when omega goes very large, this term is negligible compared to that omega squared. And then all of those power 2's would cancel with the square root. So you get omega RC over omega RC, it goes to 1. So at low frequencies, it's 0, but at high frequencies, the magnitude goes to 1, something like this. Again, it has a cutoff frequency, which is the same as 1 over RC. And you can say that if you want to make this ideal, you can say that this is like below this frequency, your filter is attenuating signals. Above this frequency, your filter does not attenuate this signal. So for omega above omega cutoff, you're good. For omega below omega cutoff, it is going to reduce the energy of the signal. So it allows high frequencies to pass and kills the low frequencies. That's why we call it a what? We call it a high pass filter. So with a simple capacitor and resistor, you can make a high-pass filter or a low-pass filter, depending on where you put R, where you put C. And you see all the analysis could simply done by the simple definition that the reactance or the impedance is 1 over C omega or 1 over Cj omega. And we can also use that to analyze the voltage in charging and discharging. All of it can be done without really directly using this relation that the voltage across a capacitor is this guy. Because we can use this one as well here. We can use this one to find the equations. But here, this one involves integral. But if I just take a Laplace domain of this, you see that V of S is, Laplace of integral is 1 over S. So it is going to be I of S over S and over C. So it is going to be I over CS. And impedance, which is V over I, it is going to be 1 over CS that we already discussed. Before I finish this video, I just remembered there was something that I didn't mention, so I just want to mention it. That is about the symbols. So if you see that in some circuits, you see this symbol. If you see this symbol, 2 parallel lines, that is a capacitor that is not polarized. For polarized ones, you typically see a straight line, a curve, and then you see a positive sign, okay? If you see that, which is on this straight side, this is a polarized one. And if you see a symbol like this, that is two straight lines, but over that you have an arrow like this, that means it is a variable one. So I just wanted to emphasize these symbols for you before I finish up the video. So hopefully the video was useful to you, and I'm going to see you in the next lecture. Thank you.